Okay, this modified code shows the initial patch made by developers. To prevent double freeze errors, the developer nullified the buffers at line 9 and at line 16, highlighted in yellow. As a result, when the buffers in or out fail to get reallocated at line 7 at line 13, they are assigned the null so that the next calls to the free are the safe at the error handling code. So this is correct fix, although it is not ideal. For example, when the buffers in fails to get reallocated at line 7, and the buffers out at line 9 is assigned the null. So it is safe to free a null point at line 22. Likewise, between the execution of the two free statement at line 15 and the 21s, the developer nullifies the buffer in at line 16. So it is also safe. Here is the first problem of the manual debugging arises. The problem is that it is difficult for the developer to be sure whether the double free errors have been properly fixed or not fixed. Now you are looking the modeled code having only 22 lines right now, but the original code for this code is at least a few thousand lines. So the developer may confuse his understanding the code and cannot sure whether these bugs are properly fixed. So indeed, this developer actually believed that a double free error still existed in this code. So to fix these imaginary bugs, which is not real bugs, the developer generated the second patches that move the free out at line 4 to at line 12. However, this change introduced a new memory leak errors where this error did not exist in the original codes. Note that when the buffer in fails to get reallocated at line 7, the buffer out is nullified at line 9. So the object that the out points to is no longer reachable, thereby introducing memory leak. This is the second problem of the manual debugging. While the developers manually fix the errors, they can introduce the new unexpected errors which does not exist in the original source code. So this memory was reported by another developer, and the original developer generated the third patches again. And to fix this memory leak, the original developer moved free out at line 12 back to its original place at line 4. Also, the developer nullified the buffer out at line 6 to prevent the imaginary double freeze. This resulting code is error-free, but it became even more redundant than the original first patches. Anyway, to fix the double free errors, it took about 1 year, and 3 patches were created, and the 3 other developers reviewed this code. In particular, this one review developer was the Linux Torvalds, who is the creator of the Linux kernels. Anyway, by understanding this real-world fixing process, I think you are motivated highly by how difficult it is to manually fix these errors. So from this slide, I will introduce Mempix, the state-of-the-art API techniques for fixing memory deallocation errors. The key feature of the memfix is that the patch generated by memfix is guaranteed to be correct. And memfix also ensures that no new errors are introduced during the fixing process. And to achieve this, the two key ideas are static analysis and solving the exact cover problems. So memfix fixed the double-free errors with the two simple changes from the original codes. First, it removes the free in from the line 15 and moved the free out from line 4 to 12. The idea is to deallocate buffers right before they get reallocated, which is the simplest patch for the original code. Furthermore, as I mentioned before, memfix formally ensures that this generated patch is always correct. As a result, it frees the developer from the error-prone task of manually verifying the correctness of the patches. To do so, memfix reduce the problem of the finding a correct patch into solving on exact cover problems. For the student who do not know what the exact cover problem is, I will briefly introduce what it is and then introduce how memfix fixes this double-free box. Okay, the exact cover problem is one of the well-known NP-complete problems. Using this example below, solving the exact cover problem corresponds to finding a subset of the set with A, B, C, D, E, where the subset contains the numbers 1, 2, 3, 4, 5 only once. So can you find such a subset that contains the numbers from 1 to 5 only once? I will give you 10 seconds. Please find such subset. Well, suppose that we select the subset ABC, but this is not exact cover because the number 2 is included twice. So suppose that we select another subset ABD with ABD, but this is the solution of the exact cover problem because the number 1, 2, 3, 4, 5 are included only once respectively. And this is the solution of the exact cover problems. Now let me explain how memfix works with these tiny codes. This code has double-free errors which occurs along the line 1 and line 7 and line 9 and 10. And more specifically, at line 1, an object is allocated and stored in pointer P. And at line 7, both pointer Q and P refers the same object, that is later deallocated twice at line 9 and 10, causing double-free errors. The goal of the memfix is to automatically fixing these double-free errors. To do so, at first, using the static analysis technique, memfix enumerate all the object traces and in this case, the first one is the trace for the object O1 that follows the true branches. And the second one is the trace for the object O1 that follows the first branches, which is along the line 1 and 6 and 7 and 8. And the last one is the trace for another object O2 along the line 3, 4, 5, and 8. That is, Memfix enumerate 3 object trace based on using the static analysis. The second step, after enumerating these object traces, Memfix tried to find safe candidate patches for each trace. For example, consider the first trace for the object O1 that follows the true branches. And after the object O1 is allocated at the first line, we can add the free statement free P after line 1 or after line 3 or after line 8 to deallocate the object. In this way, Memfix enumerate possible patches for each trace respectively. For example, for the third traces, we can add the free statement free Q after line 3 and after line 8. And then Memfix tried to remove the unsafe patches highlighted in red from the possible patches. These patches are unsafe because these deallocate the object P or Q too early before it is used at line 8, so thereby leading potential use after freeze. And we also remove the free statement at the first object trace. The intuition is to delete any unsafe free statement each trace from the other traces as well. In this case, the first free statement at the second trace is unsafe, so we also remove the first free statement at the first trace. So after removing these unsafe candidate patches, finally, Memfix tried to solve the exact cover problem like the table in the lower left. So if we choose both free P, inserting free P at line 3 and inserting free Q at line 8, we found a solution of the exact cover problems. And surprisingly, this solution also corresponds to the correct patch for fixing these double free errors. For another example, if Memfix choose both inserting free P at line 8 and inserting free P at line 8, free Q at line 8, this is not the solution of the exact cover problems. So it is also introduced the double free errors. So applying the original solution of the exact cover problems, Memfix able to generate correct patches, which is remove the double free errors. By applying the patches, inserting the free statement P after line 3 and inserting the free statement free Q at after line 8. And so that is to fix the various memory deallocation errors. Memfix employs a static analysis that collects the patch candidates for each allocated object. Second, Memfix reduced the problem of finding a correct patch into an exact cover problem over our allocated objects. Okay, let's summarize this lecture now. So I focused on motivating you by answering the question, why do we need automatic program repair techniques? And then I have introduced the two main styles of APR techniques, which are general purpose repairs and the special purpose program repairs techniques. Lastly, I focused on introducing a state-of-the-art techniques for fixing one of the prevalent errors in the OpenSUSE project, which is the memory deallocation errors. The key ideas of the memfix is to static analysis and reduce the original problem, finding the correct patches into the solving the exact cover problems. Okay, this is the end of the lectures. Thank you for listening to this lecture. So goodbye, everyone.